It's certainly my pleasure to be here, and it's been a great learning experience for me, all of yesterday. And I hope to share with you some of my thoughts and some of my experiences from a practitioner's standpoint. And I will briefly copy and cite, I should say, without belaboring it, but mention my apologies to add on to what we heard John and both Colin say in terms of my contribution. So I'll make sure that my paper gets written and turned in. But it's what I'm going to share with you is really a major transformation, aspects of major transformations that are happening within the automotive product world. And by world, I mean this in its broadest context. And so I'll share with you what I mean by the broad context. And I sort of use in the title, I use the term, "Are we there yet?" just to sort of play on a term that kids perhaps frequently say or use when they're sitting in the back seat and ask ourselves whether we've reached our destination yet. And so I'll sort of speak to that. So I'll broadly speaking touch upon some macro complexity challenges. I'll provide some contextual information and then give you a feel for some micro complexity challenges, and then speak of requirements in that context, and then provide a really brief answer. And in this, I'm using the term complexity in a fairly loose sense here, but when I say macro and micro, I mean both spatial scales as well as temporal scales. And so you really have a very tight coupling between phenomena that really are long-term in nature in terms of their creation process, interacting with entities that are relatively short-lived. And an example of a really long-term process is the creation of fossil fuel. So we pull out into a gas station and fill a gallon of gas in a few, less than a minute, but that's taken a few million years to get there in various senses. So there's a really long time scale thermodynamics at play, and then a real quick short time thermodynamics in terms of what the engine does to propel you to the next 5 miles or 20 miles or 30 miles, depending on the fuel efficiency of your product. So there's those temporal aspects at play, and then there are the spatial aspects too of what the automobile is, and how in some sense requirements in a very broad sense needs to be captured and understood. So this is a schematic that I owe to a Department of Energy website, and I'm not sure who the original creator is, so I will have to have the source somewhere, but I will cite it before we turn this in. But just as a visual, it's helpful to note, and it's sort of really humbling to also note where, in this case, the automobile as a product plays, and what enormous responsibility we have as human beings on this planet. And so we certainly are playing a small role in defining these personal mobility systems, if you will, and we're trying to figure out what the requirements might be to define those in an efficient manner, in a sustainable manner. But these automobiles are really small components of a much larger transportation system: ships, buses, trucks, trains, and what have you. And those are strongly coupled to Earth systems, to atmospheric systems, to planetary systems. And you cannot really decouple these and say, I'm going to specify requirements just for my car or my set of vehicles and ignore everything else that's happening around you. So really there are vastly different spatial and temporal scales we have to deal with, and you cannot decouple these. And I would argue that there's no single grand watchmaker here sitting over everything from what goes into our pistons and what happens out in outer interplanetary systems, if you will. So you really have to deal with the reality that you have federated watchmakers at best, and you have various systems that collect information and make them available, and you have to be able to standardize the interfaces across these macro systems to be able to do something useful. So in some sense, here's a sketch of some elements of that macro challenge, if you will. And this is clearly a systems of systems challenge. You have the physical, chemical, mechanical, electronic systems that interact with the physical, financial, and IT systems, if you will, in one sense, with human systems. And again, you cannot decouple these, and you have to be able to percolate requirements across these systems and really understand what is needed, on the one hand, to sustain the planet, and on the other hand, to make something useful and if you will, sustain the business and provide the various stakeholders with what they have really asked for, or what they might be asking for, and may not really know what that is in clear terms. From a, again, sort of macro complexity standpoint, you can look at automobiles as sort of being, and these are just cars and trucks and buses, not the two-wheelers and other motorized vehicles. But just cars, trucks, and buses, you have over 1 billion of these roaming the planet. And in computational terms, and typically these vehicles last for about 15 years. So if you really want to change a fleet, if you want to look at making an impact on a global basis, or any large single market like the United States, it takes about 15 years before most of the vehicles you see today on the roads would essentially be gone. So that's how long they typically are registered for and used for, not individual ownership, but they stay there for about 15 years. So if you want to have a big impact, say on fuel economy or in emissions, or just in terms of how we design and have impact on vehicles, speaking in terms of vehicles taken as an ensemble, then it takes about 15 years to have that impact, if you will. And in a computational sense, you can do the math here, but high-end vehicles have about 80 processors, and the argument is it's never quite clear exactly why one needs how scope and function creep resulted in having those 80 processors, and whether 80 is the right number or something less than that is in fact optimum. But clearly there's a large number of processors, there's a large number of communication networks associated with vehicles, and if you do the math, you get billions of these also essentially roaming the planet, if you will. So in some sense you have a large number of probes on wheels that can really tell us a lot about what the environmental conditions are all around the globe, and the question really is, how do we use these systems and really define our requirements so these systems become useful for more than just the single sort of private or personal transportation purpose that they might have been originally designed for. So I'm going to show you a couple of brief clips here, and I'll try to minimize the commercial aspect of it, and therefore I've removed the voice aspect of it here. See that? And my apologies if you see a few logos, but it wasn't the intent. So I could actually fast forward here. So this is what we call an adaptive cruise control system. This vehicle looks at vehicles in front and warns the driver of any oncoming vehicle in front. And so the idea here is to be able to set your vehicle at a desired cruise control at a desired speed, and then not worry about having to hit the brakes if you have a vehicle in front of you. So you basically set the vehicle to a certain speed, and then you let the radar that's sitting in the vehicle track the vehicles in front, so you can then maintain a consistent gap as you drive along. So all this is certainly adds to the driver's convenience and perhaps makes the journey more comfortable. But what happens if you have situations such as these here? This is really taking you back in history, but it's coming back to us, and I'll explain to you why. This goes back a few hundred years. It goes back 100 years, I should say. So here's a situation where this is about 80 years ago, a scene from about 80 years ago, but has interestingly enough made its way back into present times. It turns out that a highly equipped, a high-end vehicle with a lot of technology, including the adaptive cruise control technology, was on the roads not too long ago, and the driver apparently thought that this vehicle ought to be able to detect cows, and so we got a report back saying, how come the vehicle didn't respond to these objects on the road? And so it turns out that there's a certain consumer expectation and assumption here that radar ought to, that the system ought to be able to detect any object along the road, not just other cars. And so the assumption that the car makers had made clearly was that this is strictly a vehicle-to-vehicle detection problem. But basically, the end user had assumed that this is really a vehicle to any object on the path technology. And so it's really a question of how end user and stakeholder requirements are translated and then articulated to everyone involved. And so the point I was trying to make here was that while we have technology that can perhaps provide us a lot of comfort, there's often rapidly changing expectations on the part of the end user once they get used to a certain technology and make assumptions of their and change the expectations based on what they see a technology can do. So in terms of the automobile and more specifically in terms of software-related requirements, here's a schematic of some of the changes that are happening within the automotive product world. And this is again focusing on the small element of the product piece of the complexity. And I'm now sort of reducing this to not quite the micro scale, but saying at the vehicle scale, what's happening, what do consumers really observe, and what are they doing? If you look at this, most of us are used to and expect the vehicle to be consisting of sort of a set of features and functions associated with the various things that we see in the vehicle and things that we associate with cars and trucks. So those are the things that are in this sort of built-in box. And I'll briefly mention this in a slide or two. I'll give you a little more detail on what I mean. But fundamentally, these are things that you see, feel, and touch when you get into a vehicle, and you expect to see, feel, and see in the vehicle. So a steering wheel, the instrument cluster, the instrument panel, the seats, those are things that you don't carry in and out of your vehicle, and you just expect those to be part of the vehicle. Tires and the body itself, of course. So those are the entities around which the industry has sort of evolved over the last 100 years. But things have rapidly changed now with the advancements in communications and computing technologies to a point where the smartest computing entity in the vehicle is in fact not something that's built into the vehicle, but it's your cellular phone or your iPod or your iPhone that's coming in and out of the vehicle. So the smartest entity is in fact something that's brought in and not something that's built in. And so how do you really couple these built-in entities to what's brought in and define the kinds of experiences that you want to deliver, if you will, or stage? Along with this built-in group of entities, you also have content and control signals that can be beamed in. Essentially, where from a consumer perspective, you are subscribing to a service, and this could be satellite radio today, it could be something else tomorrow. It could be road payments, for example, toll payments, where you don't really carry something physically on you. Neither do you expect a box in the car doing that for you, but you have some mechanism by which an external infrastructure communicates to the vehicle, and so you have this computing that's and the associated service through communications that's really beamed into the vehicle to create the desired experience and associated services. So the three boxes on the left-hand side really show what the consumer might see. The three boxes on the top. The one on the right-hand side are things that are really invisible to the end user, for the most part, unless they fail or you have a conflict in terms of connectivity. So today, the reason why people know Wi-Fi is because either you don't have a connection when you're expecting one, or you see multiple connections and the human has to make a choice as to which one you want to connect to. Otherwise, for the most part, the end user really doesn't care about those details that's on the left-hand side. There isn't an explicit human-machine interface associated with it, and so those entities are not in the direct value proposition associated with the end user. But nevertheless, from the standpoint of being able to specify our requirements. Those are obviously the infrastructure components that are critical to the delivery of the experience. And so as planners, as designers, as decision makers, as engineers, as people working on trying to figure out how best society might adapt to these changes, we have to consider all those factors. So just sort of zooming in now on sort of the vehicle scale components and complexity. One can look at a vehicle, an automobile, and this is sort of a generic structure for almost any vehicle in terms of these functional areas, so to speak. These sort of functional areas that define what a vehicle does and how it's more or less engineered, if you will. So you have body control networks, powertrain networks, chassis control networks, safety networks. You have infotainment or multimedia networks, and then you have the infrastructure to support all these. And there's usually a gateway or two or three to make sure that the right information gets across these various heterogeneous networks, and that the mission critical aspects of the vehicle are protected from things that might otherwise not be things that otherwise might be more customized and personalized, and in some sense be vulnerable to aspects of integrity and security from an information standpoint. So by that I mean you can imagine you're coming in with your favorite ringtones and having that play on your cell phone and come through the speaker system in the vehicle when you are connecting your phone to your vehicle, but you'd really like to make sure that there's no impact on your body system, your security system, or the powertrain system when you're doing anything like that. And so these things are decoupled logically and often physically to ensure there isn't any conflict there. But I have this up here only to show that in the process of understanding what the stakeholders want and what the consumer is ultimately willing to get excited about, pay for, and come back for, and what the regulatory agencies might expect, there's a lot of different functions that have to be dealt with just within the vehicle. This is the individual vehicle, not to mention the interactions between the vehicle and the infrastructure, or the fact that you have fleet types of numbers and scales to deal with. So here's another sort of rather busy schematic of what some of these software architectural elements might look at. The key points to note here are on the one end, and that's the lowest, the last major set of words at the bottom of the page, it says Enterprise Services Interface. So what this means is that vehicle systems are often now connected to the enterprise, either for the initial sort of factory level configuration of the vehicle, configuration of the modules within the vehicle, and then the total vehicle behavior, or for upgrades at service bay, dealerships, or elsewhere. And at the other end of the spectrum, there's a set of end user application interface specifications that define how the interface between the user and the vehicle looks and feels and responds. So those are sort of two extremes, and then you have various levels of decomposition of sort of the architecture that lies between the enterprise services and the end user application interface specification, if you will. So as an example, the large systems that one has to deal with in the in-between area are energy services, energy storage and distribution, computing services, communication services, control services, and end user services, if you will. So coming down to sort of the next scale here, this is really getting to a detail. And I mentioned there were up to 80 processors in some of the high-end vehicles. Here's a rather simple, what everyone takes for granted, a simple processor sitting in the car doing essentially what each of us take for granted. What this represents is the functional sort of schematic of what one would call a central locking module. So all it does, as far as the end user is concerned, is unlocking your vehicle and unlocking the driver's door, or unlocking perhaps all the doors if you press it twice. But even that is relatively complex. Look at that. I'm just talking of one of these simple, humble modules that sit there and that have been essentially commoditized now. So you can go to the equivalent of a farmer's market and buy one of these things. But here's what it has to do. It has to respond to an ignition key. It has to be sensitive to vehicle speed. It has to be able to send crash notification information. It has to be able to adapt to valet modes keys. It has to be able to do remote keyless entry authorization. And that's using the key fob, if you will. It has to certainly do the mechanical key decoding, the driver lock, and you can read the list, but it's just it's a large list there. And this central locking module has to interact with essentially all those systems that I showed you in the vehicle level schematic. And if you understand the requirements that go into delivering a module such as this, it's actually, for me, I'm constantly surprised by the extremely high quality associated with these things. I mean, I'm always surprised at the fact that it just works all the time. And only because the number of, I mean, many of us have key fobs, and you just take it for granted. They almost never fail. And you can treat them, fairly harshly. You can place them, drop them in water, and pick them up, and they work. We place them, and when I say we, I can speak on behalf of the industry. We place them beneath tractor trailers, and if you've been up to southeastern Michigan, you see a lot of 42-wheelers, not the 18-wheelers that you see. And you can have 3 42-wheelers go essentially sequentially over these key fobs, and you can pick them up and use them. So I mean, it's interesting what kind of requirements these key fobs have, and the associated central locking system in the vehicle. But the point I'm trying to make is that at the micro level, you have a lot of these requirements, and it involves a large number of suppliers, large number of decision-making layers, and so it's very interesting. So in summary, I'd like to say that you can look at complexity and the growth in complexity of automobiles, and you see these layers of these are just examples all the way from battery chemistry up to display gauges. And to do the simplest thing in an automobile, making a slight change from a user perspective implies satisfying requirements at all these various system levels, all the way from power load, power drain, to length of wires, to antenna applications, so on and so forth, not to mention lines of code and other things of that nature. So there's clearly contextual information we need to take into account. Who are the stakeholders, the end users, the factory workers, service bay mechanics, how do we reuse that? Where do we apply these? What markets? What scale? I've mentioned much of these. And at the end of the day, what are we designing for? Are we designing really for a product? Are we designing for a service? Are we designing for a mobility experience? And as businesses, we tend to think of how we can make a reasonable profit and be sustainable. But the consumer experience has got to be relevant, otherwise we get irrelevant. And so really, people are trying to move towards trying to stage the right kind of experiences, and there's sort of various ways of approaching that, but it certainly brings into account a lot of social factors and social requirements, and trying to understand and interpret those. So in terms of requirements, there's sort of the regulatory industry kinds of requirements, many of which are expressed in legal, natural language form. There's sort of the end user business requirements that are expressed, again, mostly in using natural languages. And then there's sort of the product and environmental requirements, typically internal to the company, that are expressed at least partly using formal methods and modeling and model checking types of approaches. But those are really sparse and few and far between. They're beginning to happen, but the adoption is still not there to a large enough extent. So clearly we have a challenge understanding and interpreting requirements that are specified using different languages, notation, the different levels of abstraction. With different levels of completeness. So that's briefly speaking, are we there yet? And my answer is no, and I'm happy to conclude with that and take questions. Thank you.
May I have possibility for one? Yes, sure.
It occurs to me that there's sort of a fundamental tension when you have for the delivery mechanism or the vehicle, this 15-year lifetime. And the lifetime on some of these various elements of the experience is so much shorter. What are the dependencies that you have to expect or sort of predict or prognosticate out with respect to that? Turning back to audio, an 8-track by 1986 was laughable in a vehicle.
Right.
But it was still in a lot of vehicles that were on the road.
Right. So I guess just in very practical, in a very, very practical sense, what the industry has done is to go with what for some of these examples that involve consumer electronics, we've gone with consumer electronics interfaces. So let me give you a very concrete example. If you want to play your iPod in a vehicle today, you can play it. When I mean play it in your vehicle, control it through the buttons on your steering wheel and your center stack. You can do that today, and you connect through a USB connector. So you can go buy a product today that has a little USB connector. But 5 years ago, it would have been scandalous to mention USB in the automotive context. They would have said, hey, it wouldn't meet our 15-year requirements, it wouldn't meet our durability requirements, wouldn't meet our key life requirements. And if you wanted to do that, yes, you could do that, but you'd have to buy a $60 USB port, not a $2.99 USB port. But what we've done is we've now figured that it's okay to have that consumer port there, and really at consumer specifications, And what we have is a mechanism by which we can essentially disconnect that and replace that, perhaps every 4 years or 3 years, the way you might change your wiper blade every few years. And so essentially it's modular, and you go in there and someone says wiper blade needs to be changed, brake lining needs to be changed, and perhaps your USB connector needs a change. So there's been a rethinking of how we modularize the vehicle, if you will.
So the interface itself can...
Right, so the actual hardware can be replaced, the software can be reflashed, and these inherently have different clock speeds, if you will, compared to what sits behind them. And those are the harnesses that take the inputs from there, and the buttons and knobs that really can last for 15 years, and the displays that can last for a fairly long period. I guess Walt had a question, and then I'll come to you.
Can you say something about the requirements for the underlying operating system for these computers? And then you started to say a little bit about software updates, because of course, again, if these are long-lived vehicles, and we think of software as changing more than once every 15 years.
Right. So there's a lot of heterogeneity clearly within the vehicle system environment. In the powertrain area, we tend to we have our own operating systems that have been created internally. The cross-industry standards, but typically, I should say, these are collaborations between 1 or 2 or 3 automakers. They've sort of agreed that they want to use something called OSEC, which is an operating system for automotive electronics that was created working with some partners of ours in Germany. And so there's some of that work that happens in the mission-critical powertrain areas. In some other areas, there's a Linux-based, or I should say Unix-based real-time operating system called QNX, and Wind River has a version. So some of those are being used. In the consumer-facing arena, it's whatever makes sense. There is an embedded, there's certainly a QNX and related operating systems. There's also a Windows for mobile kind of an operating system. So a good example of that would be if you have built-in navigation systems today, those would be probably driven by whatever the supplier chooses to have, and so that's determined by scales and costs and things of that nature. So it's really quite heterogeneous. Was there a second question that you had?
About how do they deal with updates?
Oh, so
obviously you have heterogeneous software.
Right. So in terms of updates, the actual physical updates happen through, you bring a vehicle to your dealership, and then there's a reflashing process that typically connects through the onboard diagnostics port, which is mandated. The port itself is required for testing emissions and things of that nature. And so the port exists, and so through the port you can get onto something called an automotive bus, one version of which is known as CAN, or Controller Area Network bus. And so you can go through that and essentially get to where you need to go. And then there are security measures that require a physical clamp and physical IDs to ensure that the right code gets to the right place. But in some cases, every single vehicle has a unique software set that is archived. And so on the Ford side, every single Volvo is unique, if you will. The software associated with every single vehicle is separately archived and kept. And so when you go
serialized.
That's right.
John McWallen.
Yeah, hi, John.
Right, so there is a lot of research and a lot of new technology related to mobile computing.
Yeah.
Do you treat, does the automotive industry think that there's a technology that is coming up on its own and at some point it could be used, or are there any points where you want to develop it specifically for the automotive industry?
So John, when you say mobile, you mean cellular phones or those kinds of technologies? Yeah. So we know we can. What we like to do is obviously keep track of what's happening in that domain, but we don't see ourselves as sort of being able to play a very significant role there in terms of determining what happens in that industry. So we are really open to any collaboration. What we do is we release our interface specifications, and we work with the people in that industry sector and that arena to prove out the collective requirements. So whether it's phones coming into vehicles and being able to control phones, or whether it's being able to pay tolls or have automatic parking lot payments, any kind of electronic payments. So all those are happening today. Our biggest concerns there are security, privacy, and then collective usability and joint reliability. So really, if something fails, how do you ensure that there's a limp home approach, or that safety is not compromised, if you will, and that the consumer is aware of what's gone wrong, or at least where they can find help.
I think that we are enough over time, so we will have like a 15-minute break and then we will continue with the group work. Thank you very much.